Welcome to How to Succeed in ECE Without Really Trying. In this video, Dr. Victor DeBrenner will explain some complex number fundamentals.
Today we're going to talk about complex number representations. Basically, there are three types. Two of them are for humans, and one is actually less for humans and more normal. So let's talk about them. Let's talk about complex number x. Rectangular coordinates mean that we're going to write x as a plus jb, where the real part of x is a, and the imaginary part of x is b, j is the imaginary unit value square root of minus 1. The second form is polar coordinates, but we don't call it that. We really call it phasors. Phasors, we're going to have x as r e to the j theta, and to make it work, we need the rectangular to polar coordinate transformations that you should have seen earlier in your math courses. R is the square root of the sum of the squares. And the angle is the arctangent of b over a. These two are useful typically for adding or multiplying numbers in a computational sense. So those are more computational representations. So if I had x plus y, both x and y being complex, I have a plus jb, and I add to it the y, which let's just make it be c plus jd. Then we all should know that you add the x coordinates, which in this case are the real parts, a plus c, and you add the y coordinates, which in this case are the imaginary components, b plus d. If it's x minus y, then the only thing that changes is that I would have a minus c and b minus d in the form. So let's write that. Right? Okay, if I want to multiply two complex numbers, then this form is possible. In fact, this is what you would code, and x times y would be equal to a plus jb times c plus jd, which would be ac, and then j times j is minus 1, b times d. That's the real part. And then the cross terms are BC and AD. Okay. But more typically, you would think of, on paper anyway, x times y as re to the j theta times pe to the j omega, and those would be r times p e to the j theta plus omega. Okay. It's also true that in polar coordinates and phasors forms, instead of writing it so much that way, we write it as this. And so here you can think about r at theta times p at omega as being r times p at angle theta plus omega. All right, this leads to the third form, the actual number. Where now we're just using algebra and the law of exponents in algebra to do the arithmetic. This is actually, in many ways, easier, but we need Euler to recognize that re to the j theta is r cosine theta plus j r sine theta. And this actually can be proven only by Taylor series from calculus. Okay, and Taylor series in calculus is how we actually write any function as an approximating polynomial. Okay, so let's look at Taylor series for a moment. Let's start with Euler, which says e to the j theta is equal to cosine theta plus j sine theta. And let's write the Taylor series for e to the j theta. So e to the x expanded in Taylor is 1 plus x plus x squared. Well, so excuse me. Let's go back to x is j theta plus j theta squared over 2 factorial. And let's stop maybe at the third term, which will be j theta cubed over 3 factorial. Okay, now that's useful. We can expand this. Maybe I should do that now. But let's hang on for just a second. First, let's do this. cosine theta has a Taylor series, which you might recall is 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial and so forth. Sine theta has a Taylor series, theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, and so forth. And so now, if I take and substitute the cosine theta term here into here, and the sine theta term into the sine theta term, you can pretty much get that I get my result, right? The 1 j times theta, 2 factorial is theta squared, j times j is minus 1, j theta cubed over 3 factorial, j squared minus 1 minus j, there we go. And then I do that on and on repeatedly, and you see that indeed Taylor series shows that Euler works.